And now time is up and we're ready to start. So welcome to the third lecture of ISAC course series. So today we're very honored to have Professor Yifeng Xiong from Beijing University of Post and Telecommunications as our guest speaker. And his talk title would be the CRB-Rate Tradeoff in ISAC, Theoretical Framework, Limitations. So before we start, let me briefly introduce Professor Xiong. So Yifeng Xiong received his PhD degree in University of Southampton, UK, and received his bachelor and a master degree in Beijing Institute of Technology. He's currently an associate professor at BUPT. His research interests including ISAC, quantum computation and information theory, and the statistical inference over networks. He was a recipient of the 2025 HV-ComSoc and Information Theory Society Joint Paper Award and the Best Master Thesis Award of Chinese Institute of Electronics and the Best Paper Award of HV ICCC 2023. So without further ado, so Professor Xiong, the stage is yours, please.
Okay, thank you, Professor Liu, for your very nice introduction. And also many thanks to Charles Park for providing this very precious opportunity to share some of our recent works on the topic of the CRB-Rate Tradeoff in ISAC. So in this talk, I would like to share with you some of our recent results on this topic, and it will be split into three parts. In the first part, I would like to talk about the theoretical origin of the CRB-Rate tradeoff with roots in this capacity distortion theory. And in the second part, I will discuss the CRB-Rate tradeoff itself, focusing on its insights, including some of the strategies that will be achievable to these corner points of this CRB rate region, as well as two different trade-off mechanisms, namely the subspace trade-off and the deterministic-rate tradeoff. And in the third part, I would like to talk about something beyond CRB, because CRB has its own limitations. That's why we need some other sensing performance metrics, including the zip-Zarkai bound and some sensing mutual information, as well as some detection-oriented ISAC performance metrics. Okay, so let's start with the very beginning with this very conceptual figure, which indicates that given a resource budget, we could call it cost, for example, the power or bandwidth, any kind of this resource, there is going to be a trade-off between the achievable sensing and communication performance. For example, in this conceptual figure, we have the horizontal axis being the sensing error, and the vertical axis being the sum of the communication merit factor. So typically, this merit factor is going to be something like, say, the channel capacity or the achievable rate. Okay, so ideally, we like the capacity to be as large as possible and the sensing error to be as small as possible. So that's why we like to, we wish to achieve this point, right? So this is going to be the ideal point where the sensing error is minimal and simultaneously the capacity is the maximum. However, this is typically not really achievable. And the worst case corresponds to this, this line segment corresponding to boundary A, where we have to achieve the best sensing performance with the worst communication performance, while achieving the best communication performance with the worst sensing performance. So what we do is that we simply do the time sharing. We use time sharing to connect to these two extreme working points, which is the the worst case because we're not really doing any integration between sensing and communication. So in practical scenarios, we will see neither the boundary B or boundary A. The practical boundary is going to be something like boundary C, which lies in between. Okay, so this is the qualitative, a qualitative portrayal of this sensing and communication performance trade-off. So basically, our main goal is to try and characterize this boundary C, and preferably to see how we could develop a strategy that can achieve this boundary C using practical systems. So before doing that, we have to first give some quantitative characterization of this trade-off. So first of all, we have to define a cost. The cost is going to be a function of this input code word. For example, it could be the transmit power or the bandwidth or anything that relates to the resource cost of your transmitted signal. Well, we also need a sensing performance metric, which is typically characterized using this average distortion. So this is the distortion function, and we need to use to apply a average over all possible code words. So the third is that we have to consider a communication performance metric, which is actually the achievable rate, because its maximum or its supremum is going to be the channel capacity. Okay, given these formalism, what we have is that we can actually define the so-called rate distortion cost triple, which is denoted by RDB, this triple, which is called achievable if there is going to be a family of codes such that if the length of the code goes to infinity, we see that asymptotically the decoding error probability vanishes, and also the sensing distortion, the expected sensing distortion, is upper bounded by some constant D, and the average cost is upper bounded by some constant B. So this is called achievable. But if the resource budget B is given or is fixed, then we are able to discuss the so-called capacity distortion function, which is basically the supremum of the achievable rate, given that the resource budget is fixed and given a sensing performance constraint D. Okay, so this is very similar to the operational meaning of the capacity, the channel capacity itself. But what is more convenient for us to do the analysis is the so-called information meaning, right? Because for example, for the original capacity, the information meaning is to maximize the mutual information between the input X and the output Y. And this is very simple, very convenient for us to manipulate. Well, for capacity distortion, this is what we have for the operational meaning on the previous slide. And basically the corresponding information meaning is the constraint capacity under the constraints of sensing performance, this guy, and the average cost, this guy. Okay, so very similar to the original capacity formalism. And okay, there is I have to explain that there's a assumption, the underlying assumption that we assume that the channel, the communication and sensing channel, is so-called in-block memory channel, in the sense that the channel is going to be so-called the blockwise memoryless, because the channel is going to be constant for some block. This is a block for this block of time, and it's going to be constant at this block of time. But the the channels between these two blocks of times are independent of each other. So this is the basic the assumption underlying these results. For the moment, what we could do is that we could actually, or conceptually, we could compute numerically the capacity distortion region using the so-called modified Blockhart-Arimoto algorithm, because the original capacity can be computed directly using this the original Blockhart-Arimoto algorithm. So in order to compute this capacity distortion region, we have to do a slight modification to this algorithm. Okay, so let us now focus on a very simple toy model to demonstrate some of the results. So let's consider this so-called non-separate channel model, in the sense that the channel, the communication and sensing channel are integrated into one, where the communication output and the sensing output are the same, which is Y. Okay, and in the ice block, let us recall that these channels are independent across blocks. In the ice block, the output is called Yi, and the channel state, which is the parameter that to be sensed, is denoted by this eta I, and xi is going to be the input signal, the signal that is going to be transmitted through the channel, and zi is a additive white noise, which is assumed to be Gaussian. And after defining this channel model, we have to choose specific metrics for sensing and a specific form of the cost. Okay, so for cost, we assume that the cost is the average input power, which is very popular, and we choose the distortion to be the squared error. So in that sense, the average distortion, or the expected distortion, is going to be the so-called mean squared error, which is also very popular. Okay, after this very simple model, we could numerically compute the capacity distortion region, as can be seen on the left-hand side. Okay, as you can see that the so-called boundary A corresponds to the line segment, which is in the color of red, right? So this is the worst case. Well, the ideal case corresponds to this rectangular shape, which is not achievable. Instead, the achievable boundary is in the color of blue. And if you look at it, you will see that this point 1 corresponds to the extreme working point, which corresponds to the best channel capacity. No wonder the corresponding input distribution is going to be Gaussian, right? Because the Gaussian input distribution is the capacity optimal in Gaussian channels, right? So, but very interestingly, if you look at this point 4, it corresponds to the sensing optimal point, and this guy corresponds to this input distribution, which is basically a BPSK. So if you look at the modular, the magnitude of the signal, the BPSK has a constant modular, right? Its magnitude is always this constant value. Okay, if you move along this boundary from point 1 to point 4, you will see a transition between the Gaussian distribution and the BPSK, right? So this is the numerical results in this very simple toy model. From this toy model, what we could see is that there is something like a deterministic-random trade-off, right? Because in the communication optimal point, what we have is that the most random input distribution, which is Gaussian. Well, in the sensing optimal point, what we have is that it's quite deterministic, which is constant modular. It's a constant modular input distribution corresponding to BPSK, right? So naturally, we would like to try and expand and generalize this result to more sophisticated and more practical models. But it turns out that, unfortunately, this is not very possible and not very practical, because the modified Blaha error model algorithm is extremely complicated, because it relies on numerical integration on a very high dimensional space. So basically, if you consider, say, a MIMO channel, right? If you consider a MIMO channel, and if you consider that the number of transmitting antenna is NT, and if the number of receiving antennas is NR, then it turns out that the complexity is going to be exponential in the product of NT times NR, right? In nowadays, in the current communication infrastructures, this product is going to be a very large number, and its exponential is going to be extremely large, right? So that's why we're using this modified BA algorithm to directly compute the competitive distortion region is not very practical. So that's why we need to choose some other sensing performance metrics and channel models. We have to consider some specific metrics instead of this generic metrics, right? For example, if you consider sensing performance metrics, you have to consider those that are very simple in the sense that it's easy to compute, and preferably there is a closed form. And also we would like that that performance metric to be universal in the sense that it works for all sensing parameters, or you could say that it's suitable for all parametric channel models, or as more as possible, right? And the third requirement for the sensing performance metric is that it's achievable by some practical sensing estimators, because if it is not achievable for any practical by any practical method, is meaningless, right? And as for the channel model, we would also like the channel model to be simple. It's simple to manipulate theoretically, and also we would like that channel model to be more extremely general in the sense that it encompasses most of the practical channel models, right? So under these requirements, we would like to use the linear Gaussian channel model in the sense that the communication output, the output of the communication channel is going to be the this guy, which is where the H of HC is a matrix. This matrix corresponds to the matrix of the communication channel, well, the matrix HS corresponds to the channel of the sensing channel. It's also called the target response matrix in the radar literature. The target response. Okay. So in particular, we would like to have a parametric model for this matrix HS, which is the HS is a function of the sensing parameter. Say the sensing parameters could be say the velocity and the position, the range, the angle of the sensed targets, and so on. Okay. Despite its simplicity, this model is very general, because you could consider that this channel matrix could be the frequency domain model channel matrix, or the temporal domain channel matrix, or even the spatial domain channel matrix, right? So this is the simple but very general model. Okay. In addition, we made some assumptions. First of all, we assume that the channel, the signal X is a dual functional signal that is shared among sensing and communication, which is natural. And the second one is that we assume that the signal is known to the sensing receiver. As you can see on the bottom of this page, right? In the monostatic case, we assume that the transmitter and the sensing receiver is collocated in the sense that it estimates the target states using its own transmitted signal. That's why it's very natural to assume that the signal is known to the sensing receiver. Well, in the bistatic sensing scenario, we would like to assume that there is a cable connection between the transmitter and the sensing receiver, which makes the sensing receiver it makes that the receiver know that this transmitted signal by the sensing transmitter, right? But we assume that this is not known to the communication receiver, as always. Okay. After introducing this model, we would like to consider the specific sensing performance metric, which is the Cramér-Rao Bound, in short CRB. So CRB is basically a measure about the performance of unbiased estimators. So it's basically the lower bound of the variance of all unbiased estimators. But if you consider that the sensing parameter eta is random, in this case, if it is random, you cannot really have a so-called unbiased estimator, right? So that's why we have to consider the Bayesian formalism. In this case, we have the Bayesian version of the CRB, which is called the BCRB, the Bayesian CRB, which is actually the lower bound of the MSE of all so-called weakly unbiased estimators. Okay, so the CRB has its expression as follows, which is basically the inverse of the so-called Fisher information matrix. Okay, it takes this form. So that's the CRB. Basically the most important characteristic of CRB is that it's very easy to compute compared to the previous capacity distortion regions. So that's why we use CRB. This is the most important reason that we use CRB, right? But before we dig into any further details, we have to choose the specific form of CRB because there are many different possible variants of it. So basically, there are mainly three different possible approaches to formalize this CRB idea. In the first idea, we have the so-called hybrid CRB. So it treats our input signal X as a part of the extended parameter, because that parameter is basically, the original parameter to be estimated is the sensing parameter eta, right? That's the parameter of interest. But X, the input signal, is not really of interest because it's known. Okay, so that's why it's called the so-called nuisance parameter. So in the hybrid CRB, we treat X as a part of the extended parameter in the sense that you have this guy, this extended parameter. Okay, but this approach is very loose. So it's not a tight bound in the case where X is known, in the sense that it's not achievable, right? In previous slides, I have said that the achievability of the sensing performance metric is very important. So that's why we don't use this formalism. So the second possible formulation is to use the so-called marginal CRB. So basically, it integrates out the input signal in the likelihood function. But this guy cannot be used in the case where X is known. So it's also not very suitable for our scenario. So that's why we use the third one. The third one is called the Miller-Chang CRB. So basically, it computes the CRB for a given instance of X. So that's why you could say, yeah, if you could look at this guy, so you could have the say let's call this the matrix J, right? So the matrix J in this case is basically a random variable. So what we could do is that we could first compute J given X, right? We treat X as a given instance, and then what we do is that we compute the inverse of it, and then we take the expectation. So this is the Miller-Chang CRB. Okay, so it looks very simple, but it's typically difficult to be computed. Fortunately, we actually did compute this this formulation. Okay. So now we could expand. We could dig into the details of the CRB rate region. So basically, we could first define two very important corner points, namely PSC and PCS, where PCS is the communication optimal point, right? And PSC is the sensing optimal point. But these two corner points are not very equal in the sense that we know this PSC better than we know this PCS better than PSC, in the sense that for PCS, right, this is the communication optimal point. We know the optimal achievable strategy for it, because we could simply use the Gaussian input distribution, right? Also because we know the optimal input distribution, we could also compute this the y-axis, the y-ordinate of this PCS point. The only thing that we do not know is this abscissa, right? But for PSC, things are more difficult, because we neither know this y-ordinate, neither do we know this abscissa, right? We don't even know the achieving strategy for this point, because we don't know the sensing optimal waveform in general, and also we don't know how we could optimize the communication performance once we have a set of sensing optimal waveforms. So let's start with this difficult point, PSC. Before we have any possible achievable strategy, we have to analyze the CRB of this point. So we have to consider a so-called meta CRB, in the sense that it works for any possible parametric model for the sensing channel, right? The meta CRB is basically, as I have said, this matrix J is given. We could compute the matrix J given an instance of X, and then we take the inverse of it, and we take the expectation, right? It turns out that what we could do is that we could first compute this matrix J given X, and it in general it takes this form. It's basically a linear map, or an affine map of the so-called sample covariance matrix of the input signal X. Okay, so what does this imply? We can first consider. You can first consider this very simple scenario where we consider the SISO case, right? Similar to the one discussed in the sequestered distortion part. So in this case, what we have is that the sample covariance matrix Rx equals to, because it's basically a scalar, right? Is the modular square of the scalar input X. Okay, so in that case, because this function, you see, is the inverse of a matrix A, so it's convex. It's a convex function in its argument A, right? So by using the so-called Jensen inequality, what we have is that we see that the best result, the best sensing performance is achieved when the sensing performance, the sample covariance matrix is equal to its expectation. Okay, that's because this Jensen inequality. So it turns out that the sensing performance is better if the signal is more deterministic. This corroborates with our previous observations, where we see that the BPSK signals are better than Gaussian signals. Okay, so in this very simple scenario, if you consider the size of case, then the sample covariance matrix is going to be the modular square of the input signal. If you confine this guy to be deterministic, then you're going to have a constant amplitude signal, right? A constant amplitude signal, which corresponds to something like PSK right here, right? But if you consider the communication optimal point, then it's going to be the Gaussian, the complex Gaussian distribution like this. So just looking at this very simple scenario, you will see that the sensing optimal point actually loses 1 degree of freedom in the amplitude, right? The amplitude cannot be used to convey any information. So that's basically the it's going to be sacrifice some of the capability of conveying information to treat the sensing performance, right? So let's try and generalize this result to the MIMO case. So in the MIMO case, in general, we are going to have a non-scalar sample covariance matrix. So if the sample covariance matrix is equals to its expectation, then what we have is that we're going to have this matrix, this guy, to be deterministic, right? This guy is basically the product of the communication channel matrix and the input signal matrix. So this guy is going to be deterministic, and but if you do the singular value decomposition for this guy, then you will see that there is a right singular vector matrix, VHS, right? So if you multiply its complex conjugate of it, just like this, then you will see that because this right singular vector is basically a semi-unitary matrix, you're going to have V times the V complex conjugate times V equals to identity. So it vanishes in this formulation. So what does this imply? So basically, although this matrix is deterministic, we will still have some remaining degree of freedom residing in this right singular vector V. So what we could do is that we could encode the information in this matrix, right? So the remaining problem is going to try and maximize the communication rate, because we have already minimized the CRB. We have already have the optimal sensing performance. And now we are going to try and maximize the communication rate in this case, right? So that's why so in that case, we are going to choose the best input distribution for this matrix V. So it turns out that if you consider the high SNR scenario, if you consider the high SNR scenario, intuitively, this is not very rigorous, but it's very intuitive that you could say the input distribution that maximizing the capacity in the high SNR scenario is basically approximately equals to the one that maximizes the entropy, right? The most random one. So the most random one, the most random input distribution within the set of all possible semi-unitary matrices, because that's the right singular vector matrices, right? It turns out that this guy is the uniform distribution, okay? But this uniform distribution is over a so-called Stifel manifold. instead of the space of linear spaces, right? It's not really linear, it's a manifold. So there is a sampling procedure to do the sphere packing on this steeple manifold in order to do the encoding. But this is not going to be, I'm not going to give more detailed discussion on this. Instead, I would like to discuss a little bit about this corresponding high SNR capacity that is achievable by this strategy, right? It turns out that if there is no any restriction on the sensing performance, this formulation is going to be, for example, this term in particular is going to be 1, right? So that's why this term is basically the degree of freedom loss caused by this sensing restriction. Okay, so this loss basically correspond to the constraints of the semi-unitary matrices, because the semi-unitary matrices, for example, if you have this flat matrix, if it is semi-unitary, in the sense that each of its row has to be orthogonal to each other, right? So that's why there are lots of let's call this V1, right? And if we say this row is V2, then you're going to have these constraints that V1, the inner product between V1 and V2 equals to 0. Okay, so this guy will cost you some of the degree of freedoms. So that's why you have this degree of freedom loss. Okay, so this is the sensing optimal point. But if you look at this, sorry, the term T corresponds to the length of the block. Okay, the length of the block that in which the channel remains to be constant, and after that time t, or time of t, then there is another block. So in that time of t, the channel becomes different. Okay, this is a HS1 and this is HS2. Okay, so it turns out that if you prolong this time t, if the coherent time of this channel t tends to infinity, what will happen is that this guy is going to be tend to 0, in the sense that, so it suggests that if you have sufficiently long coherent time, then there is no actually there's no sensing degree of freedom loss, right? Because this can be actually interpreted by this so-called asymptotic orthogonality by Gaussian matrices, right? Because if you even use Gaussian input distribution, right? If the input matrix X is a matrix, even if it's IID Gaussian, all these entries are IID and Gaussian. If it's sufficiently large, if the t tends to infinity, then you're going to have asymptotically orthogonal rows of this matrix, right? This is actually a classical result in the literature of MIMO. Okay. So it turns out that the maximum communication degree of freedom loss is actually this guy. Okay, so this is the point PSC, which is the sensing optimal point. And now we turn to the point PCS, which is the communication optimal point. So it turns out that in this case, we do know the optimal input distribution, which is Gaussian, but we don't know in prior the sensing performance of this input Gaussian distribution, right? So it turns out that we do have this result for the sensing performance, and if you look at it, you will see that there is a very similar term here, and this guy is something that we call it the sensing degree of freedom loss. Sorry, this is the degree of freedom for sensing. Okay, So this is the sensing degree of freedom loss caused by communication. And if you come back, you will see that this guy is actually the communication degree of freedom loss caused by sensing, right? You'll see some symmetry here. So let's proceed. And if you look at this term, you will see that it's quite similar to the communication. To the sensing optimal point, right? Because if you have t tends to infinity, you will see that this guy is basically negligible, right? So when t tends to infinity, you will see that the sensing performance is also lossless, right? So because the sample covariance matrix is becomes deterministic due to the law of large numbers, right? And similarly, you are going to have this sensing degree of freedom loss depicted by this term, okay? So let's try and conclude for this moment. And what we have is that if you draw this CRB-Rate region, and you're going to have this point, PSC, and you're going to have this point, PCS. So if you move from PCS to PSC, right, along this boundary, you're going to have better and better sensing performance and worse communication performance, right? In that case, you will see that the randomness of the signal reduces because at this point, at this sensing optimal point, you're going to have the most deterministic signal. And at this point, you're going to have the most random signal, right? As you move along this line segment, you're going to have more deterministic signal. So this mechanism is called the deterministic-random trade-off. And there's another mechanism called the subspace trade-off. Because if you look at the optimal structure of the input signal, you will see that this guy is the one for the sensing optimal point. This is PSC, right? In this case, this term is the left singular vector, right? The left singular vector has to be aligned with this the sensing channel matrix HS. It turns out that it has to align with this guy. But if you align with HS, you have to misalign. You have to be misaligned with the communication channel matrix, right? If you are more aligned with this guy, then you are less aligned with this guy. Well, in the communication optimal point here, PCS, it turns out that this left singular vector is actually aligned with the communication channel matrix HC, right? So this is what we call the subspace trade-off. So basically, the signal power will move from the communication subspace to the sensing subspace, and basically the strength of this subspace trade-off can be somehow depicted by this figure, because if you have if you look at this figure, you will see that in the left-hand side here, the sensing subspace is weakly coupled to the communication subspace. So these are basically, you can say, they are orthogonal to each other, right? So in that case, once the ISAC signal moves from the sensing subspace to the communication subspace, you will lose some of the alignment. You will lose some of the alignment to the sensing subspace, but it's better aligned with the communication subspace. But if you look at the right-hand side here, this is another extreme. You will see that the communication and sensing subspaces are extremely aligned, right? They are aligned with each other. So any of this ISAC signal that is sensing optimal is also communication optimal. So you don't need to move outside of this sensing subspace to get better communication performance. So this is the subspace trade-off. Okay. So these are the two possible trade-off mechanisms in communication and sensing these two functionalities. Okay, so let's now consider a very simple toy model, which is the target angle estimation. It turns out in that case, if you consider a single target and a single user, a single communication user, it turns out that the communication degree of freedom loss is 1/2t, and the sensing degree of freedom loss is 1. And what we have is that you can actually numerically compute these points, PSD and PCS, and you could come up with some of the some of the practical strategies that are possible to achieve this line. Okay, and you can also come up with some of the outer bound, this guy, which is a bound that cannot be achievable by any possible practical strategies. But the real CRB rate region should lie between these two curves, but it's not really known. Okay, so basically what we have for now is an inner bound that is achievable by a known strategy, and an outer bound that is not achievable by any strategy, but we don't really know the real CRB rate region. This remains to be an open problem. But this does not really stops us from considering any the insights into this trade-off, because if you look at this left-hand side figure, you will see the subspace trade-off, because if you move the communication user towards the target, right, you're going to have the sensing performance, you're going to align the sensing subspace with the communication subspace, right? So in that case, if you point towards the left top corner, the communication user is more aligned with the target, then the subspace trade-off vanishes, right? And on the right-hand side, you look at the deterministic-random trade-off, which will become less prominent as the coherent time t tends to infinity, right? As t tends to infinity, you will see that the inner and the outer bound, basically they coincide with each other, and the area within these two are the possible area where the DRT takes place, right? Okay. So now we actually learned some insights from the CRB rate region and the corresponding results. And what we have is that there are two different mechanisms controlling the sensing and communication trade-off. But there are actually some limitations with this formalism. Basically, the most important limitation of this formalism comes from the part of CRB, because the rate, right? We have rate, because rate does not really have any limitation. It's quite good, but CRB is not really the perfect sensing performance metric, because CRB is not really achievable, especially in the low SNR scenarios. If you look at this figure, you will see that this line, this orange line, corresponds to the CRB of some problem. I just adopt this from one of my papers. So this corresponds to the CRB. while the blue line, this line, corresponds to the achievable MSE, the achievable sensing performance of some practical estimator. You will see that as the number of samples, if you increase the number of samples, then the SNR is actually this guy is proportional to SNR. Okay. So as SNR increases, you will see that the practical estimator performs closer to the CRB, but there's a threshold. Before this threshold, basically the practical estimator is much worse than the CRB, right? So basically in this region, this is what we call the ambiguity region on the left-hand side, the ambiguity region. In this region, the CRB is not really tight. So we do need a better performance metric in this region, right? We can actually have more detailed insights into this problem by considering a very simple problem, a very simple case of the sensing task, which is the ranging problem. So in the ranging problem, we basically estimate the distance of a target or some okay. Let us consider the distance of some target. Okay, so if we're going to estimate the distance from the target to the base station, we can estimate the propagation delay, and time. Once we have this propagation delay, we can simply multiply this delay with the propagation speed, the speed of light, right? And what we could do is that we could estimate this propagation delay from this following noisy signal, where the transmitted signal is delayed by tau, and it is corrupted by this additive Gaussian noise, N of t. It turns out that this very simple problem, in this problem, the CRB of tau is given by the following expression, right? And it's inversely proportional to SNR, and this 8 pi squared is a constant. Well, this guy, beta squared, is very important. The beta is called the so-called RMS bandwidth, which is the root mean squared bandwidth of the probing signal X. Okay, so if you're going to have the best CRB, it turns out that you're going to maximize the RMS bandwidth, right? If you're going to make this smaller, you have to have larger beta, right? Okay, so what is actually the signal that maximizes the RMS bandwidth? It turns out that it's very simple. It is a so-called the dual tone signal, right? If the signal is confined within the signal, the frequency interval, this guy, it's like this. This is a frequency. You're going to have the lower limit, FL. You're going to have a upper limit, FH, right? So on the frequency domain, this guy is basically looks like this, right? It's a dual tone. So it's just the signal, all the signal power just are packed on the edge of this frequency interval, right? So this is also called the dual tone interferometry, and in some of the ranging literature. So it turns out that this technique is very accurate only in the high SNR regime, but it's really very extremely sensitive to noise, right? So this is not going to be very useful in the low SNR scenario, but this is all actually this CRB optimal signal, right? The CRB optimal signal. So it turns out that the CRB optimal signal doesn't work in the low SNR regime. So we could learn even better by considering some technical detail, because if you think of the RFM bandwidth, if you think of it, you will see that this guy has some time domain correspondence, right? This is a quantity in the frequency domain. But if you think of its time domain, it corresponds to, it's actually proportional to the curvature of the ACF, the autocorrelation function at its peak. If you look at this figure, so this is a portrayal of the autocorrelation function. There is going to be a main peak. The main peak of it, it corresponds to the, if you look at the, say, it's a function of tau, okay? So if tau equals to 0, it's called R of tau. This is the autocorrelation function. At tau equals to 0, there is going to be a peak of it. So it's also called the main lobe. And there are going to be some lower peaks. These guys are called the side lobes. These guys are called the side lobes. So it turns out that if there are some noises, if you have some noise corrupting this signal, then the true peak is not going to be. There is some probability that the true peak is not going to be the highest level, right? It's possible that, for example, this point, because there are some noises, because of the noise, this point is right here, right? It's even higher than the true peak. So that's why the estimator will think that this point corresponds to the actual delay. So that will make you some delay estimation error, which is this guy. Okay, but there is a small probability. There's a small probability that the side lobe, right? You will see that the side lobe is much lower than the main lobe, but there is still some very small probability that this guy will be extremely high here. Okay, so this guy is also higher than the true peak. So it's possible that the estimator will choose this guy to be the estimate of the delay. So in that case, the estimation error is extremely large, right? But if you consider CRB, right, the CRB only depicts the main lobe, because the CRB is only related to the signal via the RMS bandwidth, which is also proportional to the curvature of the peak, right? It's also it only characterizes the shape of this peak, but it doesn't really care about this side lobe. So in the low SNR scenario, there is a much larger probability that the side lobes would even be higher than the true peak, right? So in that case, the CRB cannot really depict the probability. Those you will see that the error events, right? It cannot really depict the error events that the side lobe is larger than the true peak. So that's why CRB doesn't really work well. So for that purpose, we could use the so-called Zip-Zakai bound. The Zip-Zakai bound basically it reads like this, in a sense, in a ranging problem. It reads like this, where the R of X is the so-called normalized autocorrelation function, where R of X is the it's the R tilde of X, right? The R of X is the original autocorrelation function, but the normalized ACF is actually R of X divided by R of 0, where R of 0 is the level of the main peak, right? So by using this normalization, we have actually we have the main lobe level here being 1. Okay, so that's why it's called the normalized CACF. And the Q, the function Q, is actually the Gaussian error function. Okay, So it turns out that if you do some analysis, you'll see that the Zip-Zakai bound is actually convex with respect to the normalized ACF. So in that case, you can use the Jensen inequality again, just like in the case of CRB, right? So since the ZZB here, since the ZZB here is convex, what we have is that you have to use a deterministic ACF. Okay, this is ACF. You have to make this deterministic to have the best sensing performance, right? But if you consider CRB case, you don't really need the entire ACF to be deterministic. What you only need to do is to minimize the to have a fixed RMS bandwidth. What you only need to do is to fix your main lobe, right? You don't really care about the side lobes. So that's the difference between ZZB and the CRB. So it turns out that by considering the side lobes, the ZZB is much tighter than CRB. Okay, so ZZB actually fixed one of the limitations of CRB, but it doesn't really fix the problem that the results here. Right, we have actually have these two trade-off mechanisms from the CRB-Rate tradeoff, right? But since CRB is not really ideal, that's really does this trade-off mechanisms also apply to other sensing performance trade-offs? That's a very important problem, right? So it turns out that here, because the zigzag is convex, okay? It turns out that this is convex. So ZZB also has this deterministic-random trade-off. So the trade-off mechanisms works for the Zip-Zakai bound. But this does not really helps us with the other sensing performance trade-offs, right? Sensing performance metrics. So it turns out that in this case, this is a very specific case where the convexity does not work, right? Because in the previous cases, we always use the Jensen inequality to characterize the deterministic random trade-off. But in this case, the convexity doesn't work. So in this case, we're considering a detection problem. This is a detection problem. This is the sensing receiving signal model, where HS is the sensing channel, but there is a probability that there is no signal within this cell of interest, right? So there are two different hypotheses. The first hypothesis, H of 0, is there's nothing. So basically that's YS equals to W, which is only noise. And H of 1 corresponds to the case that there is some signal within this cell. So that's going to be A times E to the J of theta times HS times X plus W. Okay, so what we're trying to do is that we're trying to detect whether there's some target here or not, right? So that's a problem. But in that case, what we could do is that we could do this so-called MP detection, the Neyman-Pearson detection. So what we have is that we have this detection statistic, this guy, okay? Under this statistic, what we have is that we have this expectations, and what we could do is that we could compute the probability of detection. And we could also compute the probability of false alarm. Okay. And typically for MP statistic, for NP detection, what we do is that we make this probability of false alarm to be constant. It's a constant. But what we try and do is that we try and maximize the probability of detection. Okay. So that's why what we could do is that we could use this probability of detection as a sensing performance metric. It's natural, right? Because it's as large as possible. We would like this guy to be as large as possible, right? So it turns out that this is going to be a function also of this input sample covariance matrix, okay? But it turns out that this is not really a convex function. It's basically something like this. E to the minus 1 plus x with respect to x, right? This is not a convex function. It's neither a convex function nor a concave function. So we cannot really use the Jensen inequality to characterize the deterministic-random trade-off. So in that case, is there any DRT here? So it turns out that what we could do is that we could consider this problem from a different perspective, right? So given that there is given a distortion here, this is distortion, right? If we choose a specific distortion function here, what we could do is that we could consider the PSA point, which corresponds to the best sensing performance, where what we have is that we have this guy to be minimized, okay? This guy is minimized. So the distortion, the expectation of D of x is somehow minimized. Because in this case, we don't care about the communication performance, right? This is the sensing performance, the sensing optimal point. So in that case, the only constraint is the cost constraint here, okay? So what we could do is that we could actually draw a Pareto front for this multi-objective optimization problem, where the horizontal axis corresponds to the cost, the resource cost, and the vertical axis corresponds to the sensing distortion. So it turns out that this guy needs not to be convex, right? Because the D of x is not really it's not always convex with respect to x, and B of x is also not always convex with respect to x. So it turns out that the Pareto front is not always convex. It's something like this in general, okay? But what we could do is that we could consider that what this thing actually means, right? Because the expectation of D of x is actually, you can see that it's actually an integration. It's an integration with respect to the input distribution P of x, okay? And times D of x and dx, okay? But here, the optimization variable is actually P of x. So this guy is the optimization variable. So it turns out that this is actually a weighted average of P of x. So that's actually a linear function now of this optimization variable. So in other words, this problem, despite it looks very difficult, it's actually a linear programming problem, right? It turns out that even if the problem, the Pareto front is non-convex, it turns out that because the linear programming problem has the characteristic that its solution support is typically sparse, right? is typically sparse. It turns out that the solution corresponds to here, this point, and here, point like this. So that's why the sensing optimal point in this case is not really deterministic. The input distribution is not really deterministic, because there's a probability that it takes the position here, and there's some probability that it takes place here. But it turns out that even if it is not deterministic, its support is extremely sparse. So that's why it's still very deterministic compared to the communication optimal case. Okay. So if you look at this poor example, the detection probability, you will see that the function here, this blue line corresponds to the detection probability, right? It turns out that it is not really a convex function, because it's only convex within this region, and it's actually concave on the right-hand side, right? Okay, so in that case, what we could do is that we could find this point. This is actually the tangent point from connecting this point and the origin. Okay, you can find this point. So it turns out that if the SNR, if the SNR of the detected target is large enough, it turns out that you're going to work within this region, right? You're going to work in this region. So it turns out that you're working in the convex region. So in that case, you could use the Jensen inequality. That's why you're going to work within at a specific point here. But if you're working on the left-hand side, you're working on the low SNR regime. What you really have is that you're going to work on 2 points. You're going to work whether on the origin or at this tangent point. Okay, as you can observe from these figures, right? So in that case, if the SNR is extremely small, you're going to have a large probability on the origin. So basically, you transmit nothing. So there is a large probability that you transmit nothing, and there is a small probability that you transmit at the power of this tangent point. Well, if the SNR is larger, it's a little bit larger, and it's not larger than the tangent point, it turns out that you're going to have a small probability on the origin. You're going to transmit nothing, and you're going to have a large probability that you transmit at this power level. And finally, if you have a large enough SNR, and it turns out that you're working on the convex region, okay? So that's why you only transmit this power, okay? So in this case, you're going to have the totally deterministic transmit signal for at the sensing optimal point. So this corroborates with the results in the CRB scenario. But in these 2 points, in these 2 scenarios, you don't have the deterministic signal, but the signal is still quite deterministic because it only resides on these 2 working points, right? So in that case, we'll see that for generic sensing performance metrics, you don't really need to rely on this convexity of the performance metric. You don't really need that to be convex. But what you could do is that you could use the sparsity of the solution set, and you will see that at the sensing optimal point, the input distribution is still quite sparse. The signal is still quite deterministic, and the deterministic random trade-off still works. Okay. So this concludes my presentation today. Thank you all for listening. So if you are really interested in our works, you're welcome to read these these papers. These are our recent works on how we could actually adjust the DRT, basically on for different sensing metrics, including the side of levels and so on. Thank you again.
Okay, so thank you, Yifeng, for the very informative and very insightful work. So we do have received a number of questions, and I will pick some of them to ask you.
Okay.
So the first question, I think it's a general question. What are your views on the development of networked ISAC? How do the performance trade-off of sensing and communication differ in a networked environment?
Okay, thank you for the problem. So I'd like to say that the problem of networked ISAC is really complicated and really involved, because if you consider only the communication problem, okay, you don't really need to consider the sensing problem. If you consider the networked communication, then the network information theory itself really has a lot of open problems to be solved, right? So now if you consider networked ISAC, then the problem is going to be more difficult. So I cannot really say that anything that I discuss here can be applied to the network scenario. But what I believe is that I believe that even the problem is different, the mechanisms could be quite similar, because on the level of signal design, you have to consider the deterministic-random trade-off, right? Because even if you consider the network's ISAC case, you have to consider a deterministic-random trade-off. But the specific form of this trade-off can be quite different. So yeah, that's my opinion on this problem.
Okay, so the second question is about the robustness of the proposed theoretical framework, particularly the subspace and deterministic random trade-off. So in the real world, in real world scenarios that deviate from the idea Gaussian channels, what are the main theoretical challenges that might be encountered when extending this framework to more complex channel models?
Okay, thank you. Also, thanks the audience for this very insightful problem. So it turns out that if you just consider the CRB-Rate formalism, it turns out that the non-Gaussianity is not really a challenge for CRB, because CRB can work for any distribution that is regular, which means that it is smooth and differentiable. So for non-Gaussian cases, the CRB also works. But that is going to be quite a problem for the communication part, because for non-Gaussian channels, for non-Gaussian noise channels, the communication capacity can be quite difficult to be computed, right? So that's the main challenge in the non-Gaussian case.
Okay, thank you, Yifeng, for your answer. So there's another question. So for some sensing problems that involve severe nonlinearity and ambiguity, is there a more suitable global performance metric than CRB?
Sure. That's why we have discussed the so-called zigzag bound, right? So let me introduce a little bit more detail about ZZB. Okay, so the zigzag bound is something that originates not from the estimation theory, but actually from the detection theory. Okay, it turns out that what we could do is that we could decompose the mean squared error, which is actually an estimation theoretic quantity, into an integration of a detection error probability, which is the error probability that So basically, the error is that the probability that the error is greater than some threshold. Later, I will explain this, and times the threshold, and you're going to integrate that over this threshold. Okay, so what does this mean? This is the error probability that you cannot distinguish the true value. So say the true value is theta, the true parameter value, and some other value, the value that is theta plus epsilon. Okay, so because if there is some ambiguity in your signal, your ambiguity function is going to be things like this, right? There's a probability that you cannot distinguish this peak right-hand side with this peak on the left-hand side. Okay, so this guy is not zero, and if you use this guy to multiply your error, then it turns out that this guy is actually your mean squared error probability, right? So in that case, you're not really deriving a lower bound for MSE. This is an exact expression for MSE. But it turns out that what we could do is that we could minimize this error probability. Okay, so the minimization gives you a lower bound. So this is the Zip-Zakai bound. So despite that it's a lower bound, you will see that from this expression, you will see that this guy can a contaction problem itself is a vicinity phenomenon than CRB.
From another audience.
Okay.
So this audience said, in many application scenarios, the system requirements for sensing and communication are dynamically changing. For instance, in autonomous driving, a high communication rate is typically needed under normal conditions, but extremely high sensing accuracy is required during emergency obstacle avoidance.
Right.
So can we design an adaptive transmission strategy that allows the system to dynamically move and switch along the CRB-Rate performance boundary based on real-time task priorities or channel environments?
Well, I would say that that's quite a very important research direction to dig into. I haven't really thought about that problem, but I think that's very valuable. And I think if you are really interested in this area, then we could collaborate in the future for that problem. Thank you.
So maybe that I think the first step is to fully characterize the CRB-Rate boundary so that you can flexibly switch along that boundary. So
indeed, but that problem is already very challenging, because what we could do is that we can only have characterize the inner bound and the corner points for this region, right?
Yeah. Yes, of course. Okay, so that's all the questions from the audiences. And I would like to thank Professor Xiong again for his wonderful talk. I would like to also draw your attention to the next talk, which will be delivered by me I think it's on the 13th of October. So the Monday after the next week. Yeah. So the talk title would be Communication-Centric ISAC Signal Processing. So please stay tuned, and we will also broadcast all the live stream links. Okay, so that's all for today's talk. Thank you again.
Thank you.
Okay, bye-bye.